Hello, everyone. Today, I'd like to introduce our self-developed framework, M42, a fully modular retrieval-augmented generation framework built entirely on Java. First, let's look at our core hard indicators. We've encapsulated multiplied by 38 independent algorithm modules, multiplied by covering the full RAG workflow, from document recall, result ranking, all the way to LLM generation optimization. We also pre-built multiplied by 16 configurable orchestration pipelines, multiplied by, which can be freely combined to fit enterprise scenarios like financial Q&A, medical consultation, and general customer service chatbots. To guarantee reliability under heavy traffic, we've written over multiplied by 399 automated test cases, multiplied by, covering functional verification, pressure performance, and system robustness. The core value of M42 is simple. We reconstruct LLM application capabilities through a modular architecture, helping enterprises fully unlock the value hidden in their internal knowledge bases without modifying their existing business systems. Slide 2. RAG technology evolution and M42 core positioning. Next, let's talk about M42's core positioning and two top-level design principles. Our first core objective is multiplied by non-intrusive end-to-end optimization, multiplied by. Unlike many RAG solutions that require fine-tuning LLM weights, M42 relies purely on engineering optimization to boost full link performance. We cover 5 critical stages: retrieval enhancement, index construction, result alignment, post-retrieval compression, and final generation, forming a complete closed-loop optimization system that never touches the underlying large model parameters. Our second architectural feature is multiplied by orchestration-driven pluggable design, multiplied by. All optimization logic is split into independent, hot swappable atomic modules. We use a lightweight state machine to assemble custom pipelines on demand, with clear technical boundaries that avoid model modification. Standardized components can quickly adapt to all kinds of enterprise retrieval needs, enabling fast solution, reuse, and rapid business iteration. Here's a quick overview of our asset scale: 38 algorithm modules, 16 preset orchestration schemes, 399 plus test cases, 35 scene-based prompt templates, and 16 configurable core components. We've covered every link you'll need for enterprise RAG development. Slide 3. Java versus Python, RAG ecosystem comparison. I'm sure many of you hold the stereotype that AI development must use Python. Today, I want to break this misconception. The core of RAG is workflow orchestration engineering, not low-level model training. Whether you're calling LLM APIs or connecting vector databases, Java's ecosystem delivers mature, production-grade solutions that often outperform Python. Let's break down 3 key advantages of Java for enterprise RAG deployment. First, production stability. Spring Boot natively supports high concurrency and hot deployment. There's no need to piece together stacks like FastAPI plus Gunicorn, and it directly meets the enterprise 99.99% high availability SLA standard. Second, complete microservice closed loop. Spring Cloud delivers full capabilities for service registration, configuration management, gateway routing, and circuit breaking. Compared to Python's fragmented, scattered toolchains, it has overwhelming advantages in complex distributed systems. Third, native observability. Micrometer and JMX integrate seamlessly with mainstream monitoring tools like Prometheus and Skywalking. The out-of-box monitoring system is far more mature than patchwork Python monitoring solutions. On top of that, Java's mature ecosystem connects smoothly with vector databases, enterprise message queues, and internal security components. Spring's standardized development practices cut long-term operation and maintenance costs for teams significantly. We've fully validated this with M42. Our entire framework runs on pure Java and Spring Boot, with all 38 core algorithms and 16 enterprise solutions implemented natively. For teams with massive legacy Java assets, M42 means zero learning curve, seamless system integration, and direct reuse of existing monitoring, operation, and security infrastructure to build high-performance enterprise RAG systems fast. Slide 4. M42 Dual Module Architecture, M42 Core, and M42 Solutions. Now let's dive into M42's Core Modular Architecture, split into two core packages, M42 Core and M42 Solutions, following the stable core plus flexible plugin design idea. The core design logic is decoupling abstraction from concrete implementation, strictly following the dependency inversion principle. M42 Core is our architectural cornerstone. It only defines standard interfaces for the full RAG pipeline, BM25 retrieval, LLM invocation, query enhancement, result re-ranking, and more, plus unified data models and engine specifications. Critically, Core has zero external AI library dependencies, acting as a stable, neutral framework skeleton. M42 Solutions handles all flexible implementations. This layer contains all concrete algorithms, prompt templates, and business logic. We use Spring IOC containers to dynamically inject implementation classes into core interfaces, allowing one-click switching of retrieval algorithms, LLMs, and indexing strategies without rewriting core logic. Our standardized assembly workflow is fully Spring IOC-driven, with 3 simple steps. First, use a configuration to declare global configuration classes. Second, inject core components, LLMs, retrievers, compressors, via add bean annotations. Third, assemble these beans into complete, runnable RAG orchestration solutions. This layered design delivers high cohesion and low coupling, with full support for hot swapping and dynamic extension of all functional modules. Slide 5. State Machine Engine, Type-Safe Pipeline Orchestration. The heart of M42's flexible pipeline capability is our lightweight state machine orchestration kernel, built with only 75 lines of core functional code based on generic keys and functional interfaces. It delivers fully type-safe, stateless RAG workflow execution, automating everything from state registration to cross-stage context delivery. Let me explain how it powers complex RAG pipelines. Every step in the RAG workflow is encapsulated as an independent type state node, such as retrieve to pull documents from vector databases, generate to create candidate answers with LLMs, grade 2, score result relevance, and revise to iteratively refine low-quality outputs. All state transitions are strictly typed and stateless, making the entire pipeline deterministic, predictable, and resilient to service failures. This state machine has 3 standout features. First, full type safety. We use Java class objects as unique state identifiers. The IDE catches mismatched state logic at compile time, eliminating hard-coding runtime errors entirely. Second, fully stateless. No internal cache or storage within the engine. All intermediate data passes through a shared context map, making it naturally suitable for high concurrency and horizontal scaling. Third, register and run simplicity. The pipeline execution order is defined simply by the sequence you register each state, requiring zero extra configuration. The core value of this minimalist design is clear. We split complex multi-step reasoning logic into independent atomic state nodes to eliminate tight coupling between modules. Type safety guarantees reliable execution, even in large-scale distributed systems, with zero unexpected runtime exceptions. Slide 6. Activity Space plus Chat Model Request Template, standardized LLM invocation templates. Next, we'll cover our standardized LLM calling module, Activity Space paired with Chat Model Request Template. The core design idea here leverages the immutable object pattern to completely decouple prompt templates from business logic. This ensures thread-safe calls under heavy multi-threaded load, while simplifying configuration management calling LLMs becomes as standardized, controllable, and maintainable as invoking regular REST APIs. First, our immutable object paradigm draws on DDD value object design. All core fields are private, blocking external direct modification of object state. Any attribute update returns a brand new object copy, instead of mutating the original. The template object becomes read-only after loading, guaranteeing consistent logic across all requests. Second, we've built a standardized asset catalog, accumulated over 5+ years of industry practice. Templates are grouped by business scenario, covering mainstream RAG paradigms, including Evo and SelfRAG. All templates use unified JSON configuration files, supporting Git version tracking and team collaborative editing. Development and production environment configurations are fully isolated, with zero conflict. Prompt strategy updates take effect dynamically, without restarting the application. Third, we provide a minimalist streaming call interface with an activity space. Chainable methods like with query and with context make code clean and readable. A unified delegator component encapsulates universal retry logic and exception handling. Built-in standard result parsers cut redundant repetitive code for LLM response processing. Native compatibility with output format differences across all mainstream LLM vendors. Slide 7, Unified Entity Model and Standard Exception System. To standardize data flow and error handling across the full pipeline, M42 provides a unified entity model specification and a complete exception system, ensuring end-to-end high availability and long-term maintainability. First, we define for core entity models that run through every stage of RAG processing. First, query carrier stores the original user question and all extended metadata, acting as the pipeline's entry point for all downstream logic. Second, document encapsulates knowledge base fragments returned by retrieval, storing text content, relevance scores, and source IDs for subsequent filtering and ranking. Third, context, the global data bus of the entire workflow, linking retrieval results, query rewriting status, and generation intermediate data to keep consistent data flow across all stages. Fourth, NaiveRAG entity recognition extracts key people, organizations, terminology, and locations from queries and documents, adding semantic dimensions to boost retrieval precision. We also categorize 6 high-frequency critical exception scenarios with dedicated capture and processing logic. First, LLM call exceptions, network timeouts, authentication failures, or unavailable model services that block generation. Second, prompt construction exceptions, missing template variables, formatting errors, or context overflow, leading to invalid LLM instructions. Third, embedding exceptions, vectorization service failures or dimension mismatches that break similarity search. Fourth, NaiveRAG extraction exceptions, empty outputs or parsing errors from entity recognition models, weakening retrieval enhancement effects. Fifth, unfulfillable request exceptions. The LLM explicitly states it cannot generate compliant answers based on provided reference materials. Sixth, retrieval strategy exceptions, conflicts between multi-retrieval scheduling rules, invalid indexes, or empty recall results. Slide 8, pre-retrieval enhancement, query rewriting and pre-processing. Before executing any retrieval, M42 runs a full pre-retrieval enhancement pipeline to conduct semantic cleaning and dimension expansion on raw user queries. This solves common pain points like ambiguous user wording, colloquial redundant language, and missing key information, laying an accurate semantic foundation for document recall. This is the first critical optimization layer to lift overall RAG accuracy. We implement 6 core pre-processing strategies. First, semantic decomposition. Split long, complex compound questions into independent atomic subqueries to match scattered knowledge fragments more accurately. Second, multi-path expansion. Generate multiple query variants from generalization, concretization, and keyword extraction angles, running parallel retrieval to maximize recall coverage and avoid missing relevant documents. Third, knowledge boosting, extract entities via NaiveRAG, and combine domain knowledge graphs to fill implicit contextual information missing in the original user query. Fourth, robustness optimization via back translation. Use Chinese-English round-trip translation to strip colloquial noise, standardizing query expression, and lowering retrieval misjudgment rates. Fifth, entity anchoring. Lock core professional terms and named entities as strong retrieval anchors to improve matching precision. Sixth, noise purification. Normalize messy spoken language into standardized retrieval statements. I'll show a practical configuration example of our DMQR generalized query prompt template, which instructs the LLM to strip scene-specific modifiers while retaining the core logic of the user's question for broader recall. Slide 9. Retrieval Enhancement Full Spectrum Retriever Toolkit. Next is our Retrieval Enhancement module, which provides a complete toolkit of retrieval engines covering for mainstream technical routes, letting businesses freely balance precision and recall rate based on their own needs. First, sparse retrieval, M25 divided by TF-IDF, based on word frequency statistics. It delivers strong interpretability and guarantees zero loss of core keyword information, the classic choice for exact matching scenarios. Second, dense retrieval, semantic vector, powered by pre-trained embedding models. It captures deep semantic connections between text segments, perfectly solving synonym matching and contextual understanding problems with excellent generalization. Third, hybrid retrieval, fuses sparse and dense retrieval results with configurable weight ratios, combining the strengths of both routes to strike the optimal balance between precise hits and broad recall. Fourth, generative retrieval, hide style. LLMs generate hypothetical reference documents to guide retrieval, breaking the limitations of traditional fixed indexes and performing exceptionally well on long dependency and complex open-ended Q&A. M42 natively integrates mainstream vector databases including Milvus, Elasticsearch, and FAI-SS, with flexible Java DSL configuration to adjust fusion weights. For example, we can assign 40% weight to M25 sparse matching and 60% weight to semantic dense retrieval, then select reciprocal rank fusion as the merging strategy with just a few lines of code. Slide 10. Index Enhancement, Multi-Granular Knowledge Index System. Traditional vector storage only supports single-dimensional vector matching, so M42's Index Enhancement module builds multi-granular, semantically connected structured indexes, converting isolated documents into a logically connected, inferable knowledge network to fundamentally improve retrieval information density and deep reasoning capacity. We support 3 core indexing types. First, vector storage base index converts unstructured text into high-dimensional embedding vectors, relying on vector databases for efficient and approximate nearest neighbor search. As the underlying foundation of all retrieval logic, it delivers millisecond-level recall, even at hundreds of millions of document scale, implemented via milvavectored. Second, knowledge graph reasoning index automatically extracts entities, attributes, and relational links from documents to build structured knowledge graphs. It supports multi-hop associative reasoning retrieval, breaking single document information silos and enabling the system to answer complex relational questions, powered by HippoRAG Indexer. Third, Raptor Recursive Hierarchical Index mimics human reading logic by building multi-layer document summary trees. The bottom layer retains full original text details, while upper layers store condensed high-level summaries. During retrieval, the system locates content from coarse to fine, completely solving the industry pain point of lost context and diluted key information in long documents, implemented via Raptor Indexer. Slide 11. Alignment Enhancement, 5-dimensional full-link calibration. Alignment enhancement solves semantic, preference, and factual deviations between recalled documents and LLM generation requirements. Our multi-stage precise calibration mechanism ensures all reference materials fed into the LLM are highly relevant and factually reliable, eliminating the root cause of model hallucinations. We built a 5-dimensional full-link calibration system. First, query adaptation. Optimize the original query before retrieval, mapping it to matching semantic spaces to boost recall accuracy from the source. Second, preference filtering. Score documents by dual metrics of relevance and timeliness, automatically discarding low-quality content and only retaining high-value references. Third, self-reflection assessment. The LLM independently evaluates the factual support value of each document, filtering out noise information that cannot validate answers. Fourth, re-ranking alignment. Cross-encoder fine-ranking models reorder all recalled results, pushing the most relevant documents to the front to strengthen contextual focus. Fifth, rejection decision mechanism. After generating an answer, verify whether supporting evidence is sufficient. If confidence is low or materials are contradictory, the system rejects output to completely avoid fabricated false information. The core implementation of this calibration system is our SelfRAG dynamic reflection closed loop. The model autonomously judges for key questions during generation. Is the answer optimal? Are retrieved results relevant? Is supporting evidence sufficient? Is the output high quality? It iteratively optimizes answers based on these judgments. Practically, this module reduces LLM hallucination rates by over 40%, drastically improving factual accuracy and user trust in generated responses, upgrading RAG from passive document lookup to active, self-correcting calibration. Slide 12. Post-retrieval enhancement, re-ranking, and context compression. Before sending recalled documents to the LLM, M42 runs post-retrieval enhancement via re-ranking and context compression. This raises information density and relevance to fit the LLM's limited context window, maximizing effective reference information and avoiding window overflow. We split this into 2 core capabilities. First, result re-ranking. Cross-encoder models recalculate query document semantic similarity to resort recalled documents, filtering to retain only top K highly relevant content and lifting precision at K metrics significantly. Second, context compression. Merge, deduplicate, and distill core information from multiple documents, cutting total token consumption without losing critical details, freeing up context window capacity for more valid reference materials. 3 core components power this module. First, model re-ranker. Uses cross-encoder neural networks for fine-grained semantic re-ranking. Second, ruler ranker. Lightweight filtering via business rules like relevance, score thresholds, deduplication, and time range limits to quickly strip low-quality results. Third, compressor. Calls LLMs to summarize multiple document fragments into compact unified abstracts, maximizing core information within strict token budgets. Slide 13. LLM Enhanced Generation for generation paradigms. Moving to the final stage of the pipeline, LLM Enhanced Generation. We break away from the traditional simple query plus document concatenation mode, introducing multi-step reasoning, iterative retrieval, and dynamic decision logic to simulate human cognitive closed loops, lifting answer logical depth and complex problem-solving ability by a large margin. We support for mainstream generation paradigms. First, naive concatenation. Directly splice user queries and top K retrieved documents as LLM input. Simple and low latency, suitable for basic single-turn Q&A without complex reasoning demands. Second, adaptive judgment. Pre-judge question complexity upfront. Simple questions return direct answers instantly, while complex problems automatically trigger multi-step retrieval and iterative generation, balancing response speed and answer depth. Third, iterative retrieval. Identify information gaps mid-generation, dynamically trigger supplementary retrieval, integrate new materials into context, and loop until the dataset is complete before finalizing the answer. Fourth, Reasoning Action Loop, REACT. Simulate human think, act observe logic. Reasoning Results Guide, follow-up retrieval actions, and new retrieved observations correct cognitive bias, enabling layered decomposition and resolution of highly complex logic problems. We categorize our generation strategies into two families. First, Dynamic and Confidence Augmented RAG. Adaptive RAG switches pipeline paths based on question difficulty. Confidence RAG triggers supplementary retrieval when confidence scores drop. FLAIR proactively predicts information gaps during generation for forward-looking retrieval. Second, Cognitive Closed-Loop Chain Schemes. REACT delivers the classic reasoning action loop. NaiveRAG tightly couples retrieval and generation. RAT splits complex tasks into sequential reasoning and retrieval steps. Slide 14. Overview of 16 orchestration schemes. All the algorithm modules we just covered can be freely combined into 16 complete, production-ready orchestration pipelines via the state machine engine. Every scheme implements the unified abstract RAG solution interface, supporting one-click switching through state registration and component assembly, fully covering all business scenarios from basic Q&A to complex multi-round reasoning. We divide the 16 schemes into 4 categories. First, naive linear schemes. Simple, straight-line workflows with no conditional branches, optimized for high concurrency, low latency, basic Q&A. Representative implementations. NaiveRAG, OpenRAG, ConverRAG, BlendedRAG. Second, adaptive dynamic decision schemes. Built-in conditional branch logic that analyzes user input features to adjust retrieval strategies, weights, and recall ranges in real time. Representative implementations. Adaptive RAG, Hero Solution, Error RAG. Third, self-reflective closed-loop schemes. Add self-check and evaluation steps. The system auto-corrects answers, supplements retrieval, and regenerates outputs if low confidence or factual errors are detected. Representative implementations. SelfRAG, KeitlerRAG, AutoRAG. Fourth, evolutionary multi-round iteration schemes. Support multi-step cyclic execution, external tool invocation, and long-term context memory, built for complex reasoning, task decomposition, and long cycle planning scenarios. Representative implementations. EvolvingRAG, React Solution, FLAIR. Slide 15. Spring Boot Configuration System. All pipeline assembly and component management in M42 rely on Spring Boot's powerful IOC inversion of control container to achieve full component decoupling and automatic assembly. Every core capability, prompt templates, LLMs, retrievers, compressors, is abstracted into pluggable, configurable components, allowing developers to freely assemble custom RAG solutions from basic building blocks. Our core assembly paradigm follows 3 fixed steps. Config space solution. First, define configuration sources with a configuration annotated classes to uniformly declare global model and business parameters. Second, register core atomic components via @bin annotations, including LLMs, retrieval engines, prompt template spaces, and re-rankers. Third, assemble all registered beans into a complete, runnable RAG orchestration solution in top-level configuration classes. Underlying this is Spring's Bean Factory, an application context system, which uniformly manages object lifecycles, dependency injection, and bean scopes. System environment variables automatically map to component properties, eliminating hard coding and enabling dynamic pipeline adjustment purely through configuration changes. We've built a complete configuration matrix with over 16 core configuration classes, covering every pipeline stage. Basic model layer, basic config, chat model delegator config, retrieval enhancement layer, hybrid retriever config, re-ranker config, orchestration scheme layer, NaiveRAG, adaptive RAG, EvolvingRAG, index tool layer, Raptor indexer, Hippo RAG indexer, nurse config. Slide 16, M42 complete testing system. Quality control is a core design priority of M42. We built a full testing system to create a quality firewall for all 38 underlying algorithms and 16 upper-layer orchestration pipelines, guaranteeing system stability, logical accuracy, and consistent full link behavior under high concurrency, complex business loads. Our core testing methodology is contract testing. We define unified behavioral specifications for core components like retrievers, enforcing all implementation classes to comply with identical functional standards. This is not merely functional verification, but a binding technical contract that guarantees consistent base capabilities across all modules. In terms of testing scale, we maintain more than 95 independent module test scripts, with over 399 refined verification assertion points covering all business logic. We split tests into two major categories. First, unit tests, 23 files, cover all atomic operators including retrieval, query rewriting, indexing, and compression, verifying the correctness of every smallest functional unit to secure the bottom layer of the framework. Second, integration tests, 18 files, validate all 16 orchestration schemes and vector database interaction links, verifying the end-to-end closed-loop flow and correct transmission of complex data across all stages. Slide 17, Quick Start Guide. Now let's walk through how to quickly integrate M42 into your existing Spring Boot projects with 4 simple steps. First, import the core M42 core Maven dependency in your POM XML file, referencing the corresponding version number. Second, add import annotations on your Spring Boot startup class to load the base configuration and target orchestration scheme configuration. We use NaiveRAG config as a demo here. Third, inject the pre-assembled RAG solution via constructor injection in your business service layer. Then directly call the answer method to process user question requests. Fourth, adjust all core pipeline parameters flexibly via YAML configuration files, switch hybrid retrieval mode, enable alignment enhancement, or swap the Raptor recursive index strategy without modifying any business code. This zero-code modification configuration capability drastically reduces the access threshold for Java teams, enabling rapid POC and production launch of RAG services. Slide 18, Future Roadmap. We have 2 major development directions for M42's future iteration: algorithm, library expansion, and engineering ecosystem upgrading. First, our algorithm library scale-up plan. We will expand our core algorithm modules from the current 38 up to 78, covering every link of the full RAG workflow. Pre-retrieval, expand from 7 to 18 modules, adding query expansion, semantic caching, and pseudo-document generation capabilities. Retrieval layer, expand from 7 to 28 modules, integrating callbear, multi-vector retrieval, and late interaction algorithms. Alignment layer, expand from 6 to 17 modules, introducing RLHF alignment, LM adapter tuning, and user preference learning. Index layer, expand from 5 to 20 modules, adding composite multimodal and layered hierarchical indexes. Post-retrieval, expand from 3 to 14 modules, enriching diversity sorting and multi-document compression algorithms. LLM and orchestration, expand from 16 to 56 modules, adding intelligent agent tools, multi-step tool calling, and complex flow control. Second, engineering and ecosystem optimization. First, build standardized performance benchmark suites to quantify latency, precision, recall, and token consumption metrics, driving data-based iterative optimization. Second, complete full link observability upgrades, integrating OpenTelemetry for end-to-end distributed tracing and unified metrics collection to pinpoint performance bottlenecks rapidly. Third, expand multi-vector database compatibility, adding native support for Elasticsearch, Cadrent, and Weaviate, allowing flexible engine switching to match diverse business storage demands. Slide 19, Summary and Acknowledgements. Let's wrap up with a summary of M42's core architectural highlights and our technical foundation. Our core design philosophy is to build enterprise-grade RAG applications with modular thinking, decoupling stable core framework logic from flexible business expansion capabilities. Combined with modern Java ecosystem strengths, we deliver a high-performance, low-maintenance AI application development foundation. For core architectural advantages stand out. First, dual module separation. Decouple the stable core kernel from business extension modules to avoid core logic changes during feature iteration. Second, state machine orchestration. Type safe pipeline state transitions. Eliminate runtime execution errors caused by mismatched workflow logic. Third, immutable template cloning. The at with object pattern unifies all LLM call configuration, enabling rapid cross-scenario capability reuse. Fourth, dynamic component assembly. The config space solution assembly flow supports flexible free combination of all functional modules. Our modern technical stack foundation. Runtime layer. Spring Boot 3. Java 21 virtual threads for ultra-efficient concurrent processing. Core data layer. Jackson serialization. Native Milvus vector database integration for high-performance storage. External integration layer. OpenFame remote calls. RESTful API specifications. Modularized microservice interaction. Finally, a special thank you to all developers who contributed code, feedback, and optimization suggestions to M42, as well as all community partners for your trust and support. It's the joint effort of everyone that enables continuous iteration of this framework into a more powerful enterprise AI application development base. Slide 20, Q&A. That's the end of our technical introduction to M42 Modular RAG framework. Now, we'll open the floor for Q&A. If you have any questions regarding technical architecture, project access and implementation, or our future iteration roadmap, feel free to raise your hand and ask at any time.